Hi, Nichola from Grinds360 here. In this video, I'm going to give you a couple of tips for nailing the titration calculation. There are 10 titrations on the Leaving Cert course, and the titration experiment always comes up in question 1 on the exam paper. The titrations can be grouped into 3 types: acids and bases, redox, and water. But it doesn't matter what type of titration you have in the question, how you approach the calculation will be the same every single time, and it doesn't matter which one it is. Now, I know some of the experiments, some of them are more difficult than the others. The thiosulfate ones in particular, they are quite nasty with their colour changes, but the calculation is the same. So I'm going to go through what concentration actually is, because a good understanding of concentration actually really helps you with the titration calculation. And when we get down into the calculation itself, we're not going to use the formula that's given in most textbooks. You're actually really not supposed to be using it. Instead, we're going to work with something called first principles, which is where you track the moles. How many moles did you put in the conical flask? How many moles came from the burette? And then work from moles up to concentration. Okay, right, so let's get going. First of all, what is concentration? The concentration of something is the amount of solute dissolved in a given volume of solution or solvent. Now, we're going to do this with a few different examples. I'm going to start with the very first solution that you would have made in the lab, which was the primary standard sodium carbonate or anhydrous sodium carbonate. But as we're going through this, I'm going to keep referring to concentration as a ratio, because that's what it is. All the concentration is the ratio of solute to solution. And once you get your head around that, it actually starts to make concentration an awful lot easier. And it doesn't matter what unit you're dealing with, whether it's weight per weight or percentage weight per weight, grams per litre or moles per litre. Concentration is just the ratio of stuff you dissolved to the total amount of solution that it's in. That's it. Right, so we're going to start off with our sodium carbonate. So if I get rid of my concentration, I'm just going to move that up out of the way to give me a little bit more space. So your very first experiment with the titrations was you came into the lab, and your teacher told you to make up a sodium carbonate solution. So you put a clock glass on a mass balance and you measured out a certain mass of sodium carbonate. So in this one, I'm going to pick a mass of 2.5 grams sodium carbonate. Now, we need to dissolve that because during the titration, your experiment is carried out as liquids. So we're going to take the sodium carbonate and dissolve it in water. Now, you can't put this into a volumetric flask because the neck on a volumetric flask is too narrow. So the sodium carbonate is going to go all over the bench. So you're not going to get 2.5 grams into the volumetric flask. You dissolve it in a beaker first. So you take a beaker, you shove the sodium carbonate into the beaker, a lovely technical term. And then into there, you need to rinse the clock glass with deionized water and add some deionized water into the beaker. Now at this point, there should be exactly 2.5 grams of sodium carbonate now inside that beaker. My problem is I don't know the exact volume of the solution, but we can find that in a few minutes with a different piece of equipment. You take a stirring rod, and then you stir the solution for about 5 minutes until all of the sodium carbonate solution has dissolved. Now, when something dissolves, so inside there's my deionized water. When something dissolves, it hasn't disappeared. It has just spread throughout the liquid. So you've broken up the solid and now you've spread it throughout the liquid. Now, once your sodium carbonate has dissolved, you're going to take it, I was going to forget to change that. You're going to take it and pour it into a volumetric flask. Now, the volumetric flask in chemistry is very useful because a volumetric flask can give you a solution of exactly known volume. They have long necks, and then at the bottom, you have this rounded part, like that. Now, we all know at this stage my diagrams are shocking, so we're just not going to judge me on that. On the volumetric flask, you have a line on the neck of the flask. Now, this volumetric flask, the one that I'm saying that we have, I'm saying that it has a volume of 250 centimeters cubed. So when you pour your liquid into here and you fill it up so that the bottom of the meniscus rests on that mark when viewed at eye level, then there will be exactly 250 centimeters cubed of solution inside that flask. So we take a funnel, you put it into the neck of the volumetric flask, and then you pour your sodium carbonate solution from your beaker through the funnel into the volumetric flask. Now you need to make sure that every single part of that sodium carbonate solution ends up in here. So you need to rinse your beaker with deionized water, and then you also need to rinse your funnel with deionized water as well. So you rinse the beaker, the funnel, and the glass rod with deionized water, and you add the rinsings into the volumetric flask. Now, we have exactly 2.5 grams. So we have 2.5 grams of my sodium carbonate is in there. But we don't know what the volume of solution is yet. So we have the mass of the solute, we have the amount of the solute, but we don't know the solution yet, which means we can't know concentration yet. But if we come along and we fill this volumetric flask with deionized water until the bottom of the meniscus rests on the mark when viewed at eye level, well then there will be exactly 250 centimeters cubed of solution inside there. Then you put a stopper on it, and then you turn your volumetric flask upside down 20 times. You invert it 20 times. And what that does is it makes your sodium carbonate spread out so that your solution is uniform throughout the flask. There we go. Okay. Now, what does that actually mean in terms of concentration? Inside that flask, let's look at the ratio. So all concentration is a ratio. It's the ratio of my solute, the stuff I have dissolved, to the total amount of the solution. Okay, so based on the numbers that I have used, the total amount or the total mass of my solute is 2.5 grams. It's this over here. It's the original amount of sodium carbonate that I measured out. Then you put all of that into a volumetric flask and made it up to 250 centimeters cubed. Now, while that might not look like a nice concentration unit, that is the concentration of that solution. The concentration is 2.5 grams per 250 centimeters cubed. Now, why a lot of people won't like that is you're used to thinking of concentration in one of 6 units. So normally, when we're dealing with concentration, you're in the habit of thinking of it as percentage weight per weight, percentage weight per volume, percentage volume per volume, moles per litre, grams per litre, and parts per million, which is milligrams per litre. Now, if you look at the unit for concentration for those 6 different types or those 6 different units, it's something per something. So that's actually giving you the solute per solution. It's just doing it in different units. So like when we cover moles, I don't teach you the calculation for moles. I teach you how do you convert from mass into moles and then from moles into molecules. And we're going to be thinking of this in the same way. So if we look at grams per litre, grams, that is the mass of the solute per litre of solution. So that will give me the ratio of solute to solution. So now what I'm going to do is I'm going to move my screen over and we're going to take what we just calculated. So on the previous screen, we had 2.5 grams of sodium carbonate per 250 centimeters cubed. Now, that is a perfectly acceptable unit for concentration because it's solute per solution. However, it doesn't really mean anything to other chemists. So we're going to convert this into a unit that the examiner wants. So we're going to convert it to grams per litre. So I'm going to write this slightly differently, and we're going to do it as ratios. You have 2.5 grams of solute in 250 centimeters cubed of solution. I want what mass of solute, how many grams would be in a litre, which is 1,000 centimeters cubed. Now, when you are changing the unit for concentration, you are not changing the ratio. So the ratio of solute to solution has to stay the same. You're not adding water, you're not removing water, so that ratio cannot change. Now here, if I want to go from 250 up to 1,000, to go from 250 up to 1,000, what would I multiply? I multiply by 4. So if I'm increasing the volume of solution by a factor of 4, you also have to increase the amount of solute by the same amount. So whatever we do on the right-hand side, we also have to do on the left-hand side. I take 2.5 and I multiply it by 4. That will give me 10 grams per litre. Grams per litre. So if I go back over to my original solution over here, now we're going to keep track of our concentration underneath. The liquid that's inside that volumetric flask was 2.5 grams per 250 centimeters cubed as one concentration unit, but we've just worked out that it would be 10 grams per litre. Now, those two values for concentration are the same, because the ratio of solute to solution is the same. You haven't changed that. Even though they are different numbers, that doesn't matter. Concentration is all about the ratio. So as long as your ratio stays the same, you're fine. Now that's grams per litre. So let's have a look at another one. Another common unit that you have to get to grips with at Leaving Cert is moles per litre. So this one here on the left-hand side. Now, your moles, that is your solute, and then your litre, that is the solution. So we need to get the ratio of solute to solution in moles per litre. Okay, now I'm going to move this just down another bit to give me enough room. Okay, now I'm going to go right back to the start. So we know the concentration is 2.5 grams in 250 centimeters cubed. I want to figure out what my concentration is in moles per litre. Now, I would recommend doing this in 2 steps. So first of all, we're going to start with the solute. Now, at the minute, my solute is in grams as the unit. I need to convert grams into the unit that it's asking me for the solute, which is moles. So how do we get from grams to moles? You need to use your moles conversion, which we learned about in moles. So if I just move over here to the right-hand side, your moles triangle is this, where we have moles, mass, and RMM. Now, some of you might call the relative molecular mass MR. It is the same thing. I just don't like learning off another abbreviation when I can just call it the RMM. It's fine. Right, so here, we're trying to find the moles. We know the mass because that's given to us as 2.5 grams. That's the amount of the solute. But we don't know what the RMM is. So we're going to calculate that. Now, the relative molecular mass of whatever the substance is, which is sodium carbonate. Now for this, you have 2 sodiums, so it will be 2 multiplied by 23 plus 1 carbon, so it's 1 times 12, which is 12, plus 3 oxygens, 3 multiplied by 16. On your calculator, when you add those numbers together, you're going to get a value of 106 grams per mole. Now, that is the relative molecular mass of sodium carbonate. So that's the number that we're going to use when we convert grams into moles. Now, for my number of moles, that is my mass divided by the RMM. Now, it's not necessary in the exam to write the formulas like this, but if it helps you, write them in. My mass is 2.5 grams, and my relative molecular mass is 106 grams per mole. Now, when I type that into a calculator, when we type that in, we're going to get a bit of an awkward number. So that is, I don't like to leave it as fractions, 0.023584905 moles. Now, I'm going to give you a bit of advice here. When it comes to the calculations in chemistry, never round your answer until the very, 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 very end. When you're doing a titration calculation, you're going to have to do at least 5 different steps in the calculation. And if you round early, well, then you're going to start dropping marks very quickly. So don't round until the end. I'm going to leave that number on my calculator as it is. And any operation that I do to this number, it's going to be the number that's on the screen. So don't round that. Now let's go back up to this bit here. So what have I just done? At the minute, all I've done is convert that. So my 2.5 grams of sodium carbonate, I now know what that is in moles. It is 0.023584905 moles. Now, I haven't changed the amount of solute. You have just changed the unit. So it's still in 250 centimeters cubed. Now, at the minute, my ratio is in moles per 250 centimeters cubed, and I want moles per litre. So what I'm going to do now is I'm going to work out if I want to bring this up to how many moles would be in a litre, which is 1,000 centimeters cubed. How do you get from 250 up to 1,000? You multiply by 4. If you are increasing the volume of the solution by a factor of 4, you have to do the same thing to the solute. To keep the ratio of solute to solution the same, whatever you do on the right-hand side, you also have to do on the left-hand side. So we take our number of moles and we multiply by 4, and that's going to give me 0.094339622. And that's how many moles are in a litre. Now at this point, if that's the final part of the calculation, you can round that to possibly 0.094 would be fine. That's what I would round that to as moles per litre. Now if I go back to what my original solution is up here, my other unit, so I've now worked out that another unit for this is 0.094 moles per litre. Now, despite the fact that these 3 values for concentration, the numbers are all different, it doesn't matter. The ratio of the stuff I dissolved to the liquid that's inside that volumetric flask is the same. We're just converting it into different units. Now, another common one would then be to work out weight per volume. So you take your grams per litre and you divide by 10 because it's grams per litre to grams per 100 centimetres cubed. So you're going from 1,000 down to 100, you divide by 10. And we'll see that in a few minutes when it comes to doing one of the titration calculations. Now, if I move this over here, let's talk about what happens in the titration itself. So when you're doing a titration, you spend ages making up your primary standard solution. Then the fun begins. You come along with a pipette. You rinse the pipette with deionized water and you rinse it with your sodium carbonate solution. Then you fill the pipette with the sodium carbonate solution until the bottom of the meniscus rests on the mark when read at eye level. And you transfer the liquid into the conical flask using the pipette. Now, pipettes are designed to deliver a certain fixed amount of liquid. So if this delivers 25 centimeters cubed of the sodium carbonate solution into the conical flask, all you have done is moved your liquid from one place to another. The concentration has not changed. When you move the liquid from one place to another, the concentration stays the same. The only way the concentration is going to change is if you add water or remove water. So here, the concentration of what went into that conical flask is the same as the volumetric flask. So we know that it is 0.094 moles per litre. Now, inside that conical flask, there isn't 0.094 moles of sodium carbonate. It isn't 2.5 grams because you're only taking a very small amount of it and putting it into the conical flask. You're taking a tenth of it basically. So inside there, if I want to figure out the total number of moles that went into that conical flask, because that's what you need for your reaction. We're following moles through this. I want to know exactly how many moles did we put into that flask. So you start with your concentration of 0.094 moles per litre. That's how many moles are in a litre. I want how many moles did we put into that conical flask? What volume did we put in the conical flask? We put 25 centimetres cubed. So I want how many moles are in 25 centimetres cubed. To get from 1,000 down to 25, you divide by 40. Now this might be a little bit foreign to some of you who are used to using the formulas. I don't like using formulas here because I find if I teach this with formulas, students start sticking numbers into formulas and they don't understand what they're doing. Whereas I prefer to do this with ratios. So I'm going from 1,000 down to 25. You can either divide by 1,000, that's how many moles are in 1 centimetre cubed, and then multiply by 25 to bring it up to 25 centimetres cubed. That's the same as dividing by 40. If you're not sure, put 1,000 on your calculator and divide by the volume that we're trying to get to, which is 25. That's 40. Whatever you do on the right-hand side, you have to do on the left-hand side. So I take 0.094 and we divide by 40. Now, I know I cheated a little bit where I rounded this. We're just going to go with it. Normally, I wouldn't. And that's going to give me 0.00235. That's the number of moles inside the conical flask. Now, if we're doing reactions, this is where your molar ratios from balanced equations are really, really, really important. Let's go back up here. And we just get rid of this. Now at this stage, I'm just going to clear what's on the right-hand side of the screen because I don't need it anymore and I don't want it cluttering up the screen on me. So your very first titration that you would have done in the lab is you would have taken your sodium carbonate, which we now know exactly how many moles are in there, and you titrate it against an acid. So it's a weak base, you titrate it against a strong acid, and your acid goes above in the burette. The acid that you would have used was hydrochloric acid. So the balanced equation for this reaction would have been sodium carbonate reacts with HCl, and we form a salt, which is sodium chloride, plus carbon dioxide, plus water. Now I need 2 of those and 2 of those. And then everything else should balance, and it does. Now, for this balanced equation, I don't really care about what's on the right-hand side. I'm only really focusing on what's on the left, so this bit here. So I'm going to move this up so that the rest of the equation is behind the picture of me, but we don't need it anyway, so it doesn't really matter. So I'm going to leave it like this. Now, when you come along and open the tap on the burette, you add the acid into the sodium carbonate with swirling, rinsing down the sides, and there was an indicator which was methyl orange was added as well. And you stop adding the acid when the colour change is observed from yellow to red. Now we need to know what volume of the acid was added in, which you read from the burette. Now I'm gonna pick a number out of the sky. I'm gonna pick 8.6 centimeters cubed. Now we can use this to figure out what the concentration of the acid is, because what titrations have in common is a very, 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 very specific fixed volume of one liquid is reacted with a fixed volume of another liquid. More specifically, you are reacting exact numbers of moles. Now, when you did stoichiometry 2 or moles with the limiting reagent, you would have learned from other reactions that usually one reactant is in excess and the other one is the limiting reagent. When you have a titration, they are both the limiting reagent. That's why your teacher probably killed you to make sure that you're going drop by drop by drop. It's like watching paint dry, I know. when you're adding the acid from the burette, because you don't want to go too far and add too much liquid into the conical flask. So here, because I know the exact number of moles inside that conical flask, I know exactly how many moles of sodium carbonate is inside the flask, and it's that exact number of moles of sodium carbonate that we can use to figure out the moles of the acid that was added. So if I go over here, from my balanced equation, we need the ratio of sodium carbonate to HCl. Now that ratio from the balanced equation, there's a 1 in front of the sodium carbonate and there's a 2 in front of the HCl. Now what that means is when 1 mole of sodium carbonate reacts, it needs 2 moles of hydrochloric acid. However many moles of sodium carbonate you have, you need twice the amount or twice the number of moles of the acid. Now, inside that conical flask, we know exactly how many moles of sodium carbonate is in there because we worked it out at the bottom of the screen. There is 0.00235 moles of sodium carbonate in there. Now, if you've done the titration correctly, there should be twice as many moles and not more of acid added into the conical flask to get you the colour change. So if I have that number of moles of sodium carbonate, I need to multiply that by 2 to get the moles of the HCl, which is 0.0047. Now, what that number tells me is when 8.6 centimeters cubed of HCl is added into the conical flask, inside that 8.6 centimeters cubed, there was 0.0047 moles of HCl. Now you have the ratio of solute to solution because you have the amount of the solute and you have the amount of solution that you added. So for the HCl, your ratio of solute to solution is 0.0047 moles, and the amount of liquid that number of moles was in is 8.6 centimeters cubed. If I want to figure out what that concentration is in moles per litre, moles in 1,000 centimeters cubed, to get from 8.6 up to 1,000, that's not the nicest of ratios. So what we're going to do is we are going to do this in 2 steps. So you take your 8.6 centimeters cubed and you bring it down to 1 centimeter cubed. How do we get from 8.6 down to 1? Well, you divide by 8.6. Whatever you do on the right, you have to do on the left. So we take the 0.0047 and we divide by 8.6, and that gives me 0.000546511 moles in 1 centimeter cubed, but I don't care how many moles are in 1 centimeter cubed, I want moles per litre. To get from 1 up to 1,000, you multiply by 1,000. And then whatever we do on the right, we have to do on the left, which is going to give me 0.54651, or a nicer number for that would be 0.547 or 0.55 molar HCl. And that's how we're going to use this idea of the ratio of solute to solution to work from one reagent whose concentration we know to another reagent whose concentration that we don't know. Now, that's the basic idea of concentration. Now, we're going to apply what we have just learned to a couple of exam questions. We're going to do 2 of them. Now, we're going to do these 2. So the first one is from 2024. This was the exam question that came up last year, and it was about vinegar. Now, for this one, let's have a look. Okay. Now, so from 2024, let's go down through this. Now, I'm not going to do the full exam question because the rest of it, it's not that important. But the calculation for this is what the skill is that we're trying to get from this class. How do we do the calculation? Now, for this, I'm going to highlight the important numbers throughout this question, because these are the numbers that I'm going to use when it comes to the calculation. So we're going to start from the very top and highlight what's important. A student carried out an experiment to determine the concentration of ethanoic acid in vinegar. Fabulous. 10 centimeters cubed, that 10 centimeters cubed is important. Of vinegar was first diluted to exactly 50 centimeters cubed, that's important. The diluted vinegar solution was titrated against 0.09 molar, that's important, sodium hydroxide in a conical flask. On average, 12.4 centimeters cubed of the diluted vinegar were required to neutralize 25 centimeters cubed of the sodium hydroxide. All of those numbers, those 5 numbers that I have highlighted on the screen, you're going to have to use them in your calculation. Now, what can be sometimes daunting about the titration, particularly the nastier ones like the thiosulfate ones, they usually bombard you with lots of information. So I don't want to be reading this titration question 5 times to pick out what's important. When I read through this, I'm going to highlight the numbers that are given because they're the numbers that I'm going to be using in the calculation anyway. Now we go down to question D. Part 1. Calculate the number of moles of sodium hydroxide in each 25 centimeters cubed portion. Now, what I'd recommend doing before you launch into the calculation is this. Write out the balanced equation that's given in the question. Now, in the titrations, you will always be given the balanced equations, so don't learn them off because that's nonsense. You will be given them. So the one that's written on the screen is, I have CH3, COOH, my ethanoic acid, reacting with a base, which is sodium hydroxide. And we form a salt plus water. Now, the numbers that I highlighted, I'm going to write them underneath the relevant substance from the balanced equation. So, I highlighted, I'm going to ignore the first 2 numbers, I'll use those at the end for the dilution factor, I'm not going to use them now. So, for ethanoic acid, how much of it was used in the titration itself? That was 12.4 centimeters cubed. That's the volume that's added from the burette. For the sodium hydroxide, the concentration was 0.09 molar, and the volume of it was 25 centimeters cubed. Then, you're asked to work out the moles of sodium hydroxide in each 25 centimeters cubed portion. Okay, let's start with that. Now, when you're looking at these numbers, and you're like, oh my God, where do I even start? You always start with the thing where you know both the concentration and the volume. You have those 2 pieces of information, which means you can work out the moles. Now, if I was to draw myself a little diagram, the way we did the last question. Inside that conical flask, there is 25 centimeters cubed of solution of 0.09 molar sodium hydroxide. Now, we know the concentration of the sodium hydroxide is 0.09. That's how many moles are in a litre, because 0.09 molar, capital M, stands for moles per litre. So I have 0.09 moles of solute in a litre of solution. Now for part 1, we're asked for the moles of sodium hydroxide in 25 centimeters cubed. Well, if that's the moles in 1,000 centimeters cubed, I want how many moles are in 25 centimeters cubed. So how do I work it from 1,000 down to 25? To get from 1,000 down to 25, you divide by 40. You can divide by 1,000 and times by 25, it's the same thing. Whatever we do on the right-hand side, we have to do on the left, because all we've done is moved your liquid from one place, the volumetric flask, into the conical flask. You haven't changed the concentration, you have just moved it. So whatever we do on the right, we have to do on the left to keep that ratio the same. So 0.09 divided by 40 is 0.00225 moles. Now, that is the number of moles, 0.00225 moles of NaOH inside that conical flask available to react. Now, in the exam, that was your first 4 marks in 2024. Now next, we're going to take that information, and now the next step, you've done everything you can for the sodium hydroxide, you've worked out the number of moles. Now that's the known. We're going to use that to find the unknown. So my next step is to start working towards the ethanoic acid. And question part 2, calculate the moles of ethanoic acid in, important, each centimetre cubed. So if we read that again, in each centimetre cubed, that means in 1 centimetre cubed. Lots of people miss that in 2024. So we're looking for moles of CH3COOH in 1 centimetre cubed. Now, at the minute, that information that I have, that's for the sodium hydroxide. So we need to now bring it to the ethanoic acid. So if we look at the top of the screen, we are now finished with the sodium hydroxide, and now we're over here starting to look at this, the ethanoic acid. Now I'm putting an X through the NaOH like that for a reason, because one of the common mistakes here is students pick the wrong volume that we're going to work towards. Right, from the balanced equation, we need the ratio, because when you add from the burette into the conical flask, we know from the information given that 12.4 centimetres cubed is added into the conical flask. But we don't know how many moles are inside that 12.4, and that's what we're working out. So from the balanced equation, the ratio of the sodium hydroxide to the ethanoic acid is 1:1. There's a 1 in front of the ethanoic acid and a 1 in front of the sodium hydroxide. That's a 1:1 reaction. If you start with 1 mole of sodium hydroxide, you will need 1 mole, the same number of moles, of ethanoic acid. Now, up above, we worked out a minute ago that there's 0.00225 moles of sodium hydroxide inside that conical flask. So in order for this to be a titration, the total number of moles of ethanoic acid that's added into the conical flask to see the colour change is the same, because it's a 1:1 ratio. So that means I've 0.00225 moles of my ethanoic acid. Now up here, let's look back up at the conical flask. When the ethanoic acid is added in the amount of liquid that's added in, there is 0.00225 moles of the ethanoic acid. Now, in order for us to add that number of moles of acid, that's the volume that was added to give us that number of moles. Therefore, we now know what concentration is. So let's move that down. Now here, let's move to the ethanoic acid. So I have 0.00225 moles of ethanoic acid in 12.4 centimetres cubed. A common mistake here is to say that it was 25 centimetres cubed. It's not. The amount of the acid that was added from the burette was 12.4 centimetres cubed. We're asked how many moles were in 1 centimetre cubed per centimetres cubed. So we need to get from 12.4 down to 1. We divide by 12.4, and whatever we do on the right, we do on the left. So 0.00225 divided by 12.4, that is 0.000181451. Lovely awkward number. If you put that as 1.81 by 10 to the minus 4, that's absolutely fine. That was an acceptable answer. Now for this, in order for us to get 0.000181445, that is our next 4 marks. Now, part 3. Calculate the concentration of ethanoic acid in the original vinegar in moles per litre. Now, what was added into the conical flask was the diluted vinegar. So we're going to find out what the concentration of that is first, and then we'll worry about the rest of it. So from what I calculated in the previous part, there is 0.00225 0.0018141 moles in 1 centimetre cubed. I want how many moles are in a litre. So how do I get from 1,000 or 1 up to 1,000? You multiply by 1,000. Whatever you do on the right-hand side, you have to do on the left-hand side. So you take your number of moles and you multiply by 1,000, and that's going to get me 0.181451 moles per litre. Now you're not finished with that. That is actually the concentration of the dilute vinegar. And for that number there, the examiner gave you 2 marks. But that's the dilute. Now during the experiment, you took the original vinegar and you added water to it. So we diluted it. And what the dilution factor is, you were told in the very beginning of the experiment, 10 centimetres cubed of the original vinegar was diluted up to 50 centimetres cubed. So the concentration of what you used in the experiment is less than what the original was because there's 40 centimetres cubed of water mixed with it. Now for this, in order for you to work your way back, you need to know what the dilution factor is. And to work it out, you put the final volume when you were diluting it, which is 50, over the volume of the original, which was 10. So 50 divided by 10 is 5. Now what that number means is the solution of ethanoic acid that was used in the experiment is 5 times less concentrated than the original. To work my way back to the original is 5 times more concentrated than what we used in the experiment. Now we know that the concentration of what we used in the experiment was 0.181451 molar. To find out what that is in the original, you take that and you multiply it by the dilution factor, which is going to give me 0.907258 moles per litre. Or if you prefer, now we can put that as 0.907 molar. And for working out 0.907, the examiner gave you 2 marks. We're nearly there. Now the last part, which is part 4, calculate the concentration of ethanoic acid in the original vinegar in percentage weight per volume. Now when I had a strong suspicion vinegar was coming this year, I had everybody warned, make sure you can do this conversion, which is from moles per litre to grams per litre to weight per volume. So this conversion, when you go from moles per litre to grams per litre, you take your moles per litre and you multiply by the relative molecular mass of what the compound is. And then to go from grams per litre to percentage weight per volume, you just divide by 10. Now, I wouldn't recommend combining this all in one formula. Do it in the 2 steps. From the previous part of the question, we know that the moles per litre is 0.907. Now, we need to multiply that by the RMM of what the compound is. So what is the chemical that is the concentration of? It's ethanoic acid. So if I just move that over there, because I don't want to keep moving it to the right. So here, ethanoic acid is CH3COOH. We need the relative molecular mass, or the MR of that. There's 2 carbons, so it's 2 times 12, plus 4 hydrogens, 4 times 1, plus 2 oxygens, which is 2 times 16. When you add all of that together on a calculator, you're going to get 60 grams per mole. Now, I remember that it's 60 grams per mole, but you should be working it out on a calculator. And before anybody goes, do we need to show the RMM calculation? Yes, you do. Now, I know I'm giving you the scary eyes here, but it's really important that you show the calculation. This was one of the most common mistakes on the 2024 exam, were people making a pig's ear of adding those 3 numbers together. Now, if your examiner can see the calculation and they know that you've put the right numbers in, but you've come up with, say, 58 instead of 60, well then your finger slipped on your calculator when you were adding them together. So you'll be deducted 1 mark for a slip. But if you don't show how you arrived at the RMM and then you just use 58 as the RMM, I'm not going to give you any marks for that. I can't because I don't know where that number came from. So if you want slip marks to bulk up your numbers or bulk up your marks in a calculation, make sure you show all of the workings. Now back over here. We take our moles per litre and we multiply it by 60 grams per mole. Now when you multiply those two together, your moles cancels with moles, and that leaves me with 0.907 multiplied by 60, which is 54.42 grams per litre. Now, to get your percentage weight per volume, you take 54.42 and you divide by 10. And that's going to give me 5.442% weight per volume. Weight per volume, remember, is grams per 100 centimetres cubed. So if I just go over here to the right-hand side, you have how many grams are in a litre. We want how many grams are in 100 centimetres cubed. So to go from 1,000 down to 100, you just divide by 10. And that's where that divide by 10 came from. Now, and that is your final answer that the examiner has asked for. And for 5.44, they're going to give you 3 marks. Then for using 60 up here as the RMM, the examiner gave you 2 marks. And that's how you do that titration calculation. Now, they're all exactly the same. You're not going to believe me yet. Every single titration question calculation is the same. Now, to prove that, we're going to do another one. So the second one that I want to have a look at is from 2015, question 1. And I deliberately picked this one. It's a thiosulfate, the standardization of sodium thiosulfate. This question hasn't been seen since 2015. Other thiosulfate experiments have come up, but this specific one hasn't been seen since 2015. Right, now this one. The thiosulfate ones, when people see this, it tends to put them off because yes, it is a little bit tricky. But it's the same thing as the last one. So let's read through it. Sodium thiosulfate is a reducing agent that reacts with iodine according to the following balanced equation. To determine the concentration of sodium thiosulfate solution, a student titrated against 25 centimeters cubed portions of the standard iodine solution. Now that 25 centimeters cubed is going to be important. Then we read down, we go down to part D. Given that there were 6.35 grams of iodine in 500 centimeters cubed, that is giving you the concentration of the iodine. It's 6.35 grams per 500 centimeters cubed. Calculate the number of moles of iodine in each 25 centimeters cubed portion. Okay. Same rules apply here. Whenever you're doing a titration, the first thing you do is you write out the balanced equation on the paper. And then we're going to fill in the numbers underneath each substance. We have I2, so my iodine, reacting with thiosulfate to give me 2I minus plus the tetrathionate, which is S4O6 minus 2. Now you won't have to write that balanced equation in the exam, it will be given to you. So from what we know that the concentration of the iodine is 6.35 grams per 500 centimeters cubed. The volume of the iodine solution that was used was 25 centimeters cubed. Based on other information, we'll find out in part 3, if I highlight it now, that 17.85 centimeters cubed of the thiosulfate was used. Perfect. Now, based on what we did before, you're looking for the thing in the balanced equation where we know both the concentration and the volume. So in that case, we have to start our first principles calculation here with the iodine, because even though it's an awkward unit for concentration, we do know what the concentration is and we know the volume of it. So in part 1, where it's asking us to find the number of moles of I2 in the volume that you used in 25 centimeters cubed. Now your concentration, we have 6.35 grams of iodine in 500 centimeters cubed of solution. Then we're going to have to work out how many moles are in 25 centimeters cubed. Okay, so what I'm going to do is I'm going to take my solute in grams and we're going to convert that to moles. So our moles equation, let's move that out of the way. Your moles triangle, we have moles, mass, and RMM. I have the mass, so I have this number here. I'm trying to find the moles, but in order to do that, I need the RMM. So now, to find the number of moles, that will be the mass divided by the RMM. So it's going to be 6.35 grams of iodine. Now we need the RMM. So it's the RMM of what the molecule is, which is I2. Now this one's a little bit tricky and you have to look up what the RMM or the atomic mass of iodine is on the front cover of your exam paper. Now for this one, iodine is 127. And because the formula is I2, it's going to be 2 multiplied by 127, which is 254 grams per mole. So it's 6.35 divided by 254 grams per mole. When I type that into my calculator, 6.35 divided by 254, that is 0.025 moles. Now, if I go back over here, all I've done by doing that is I have converted that mass into moles. So now, instead of thinking of it as 6.35 grams of iodine, we now know that it is 0.025 moles. We still haven't changed the amount though. That's the number of moles in 500 centimeters cubed. Now, if that's the number of moles in 500 centimeters cubed, that's not the amount we're using in the experiment. I want how many is in 25 centimeters cubed. So I need to get from 500 down to 25, which should be divided by 20, but I'm just going to double check. Yeah, so we're going to divide by 20. And whatever we do on the right-hand side, you have to do on the left. So we take our 0.025 and we divide by 20. And that's going to give me 0.00125 moles. That's the total number of moles of iodine inside the conical flask for the titration. Now for this, where's my marks? Now the examiner is going to give you 3 marks for working out the number of moles of the iodine that was inside the volumetric flask, which was 3. And then when you transferred the liquid from the volumetric flask to the conical flask as 25 centimeters cubed for 0.00125, that's the other 3 marks. Now that's part 1 done. Next, part 2. Part 2, calculate the number of moles of sodium thiosulfate required to reduce this quantity of iodine. Now we are done with the iodine, now we're moving towards the thiosulfate. So if I go back up here to my balanced equation, we're now finished with this, and now we're over here with the thiosulfate. So now we're looking at this volume. Be careful here. So now, from that balanced equation, there is a 1 in front of the iodine and a 2 in front of the thiosulfate. So that is a 1:2 reaction. So we put the ratio of what we know, which is iodine, to what we're trying to find, which is your thiosulfate. From that balanced equation, that is a 1:2 ratio. The number of moles of iodine we worked out in the previous part was 0.00125. Then to find out the number of moles of your sodium thiosulfate, it has to be twice as many. So you times it by 2. And that gives me 0.0025 moles. And for that number, the examiner is going to give you 3 marks. Now, that's part 2. Part 3. Calculate the concentration of sodium thiosulfate in moles per litre. If 17.85 centimetres cubed of which were required. So now we have the volume. Now here, we added in 0.0025 moles of sodium thiosulfate. But what volume was added from the burette to give us that number of moles? Now, if you're not sure, it's actually given in the same question, but we wrote it down here. It's this number here. It's 17.85. And it's why I write the numbers underneath the substances in the balanced equation. So that when you get to this step, when you're moving from the thing you know to the thing that you're trying to find, that you know what volume that you're dealing with. It can't be 25 centimetres cubed because that's the volume of the iodine solution, not the thiosulfate. Now if we go back down. So I know that I have 0.0025 moles in, what was it, 17.85 centimetres cubed. Perfect. That's how many moles are in 17.85. I want how many moles are in a litre, because that's what it's asking me for. To get from 17.85 to 1,000, that's a bit of an awkward ratio. So let's go down to 1 centimetre cubed in between. From 17.85 down to 1, we divide by 17.85. Whatever we do on the right, we have to do on the left. 0.0025 divided by 17.85 is a lovely number, 0.000140056. That's how many moles are in 1 centimetre cubed, but we want how many are in 1,000. So then we take our moles and we multiply by 1,000, which is 0.140056. So 0.14 moles per litre. Now here, this is a 6 marker. For the bit in the middle, for working out how many moles are in 1 centimetre cubed, the examiner gives you 3 marks. And for working out 0.14 moles per litre, they'll give you another 3 marks. Now it's worth saying here, if you've worked out that the concentration is 0.14 molar and you didn't show that one in the middle, you'll still get your full 6 marks. It's just a little bit dicey though if you've made a mistake, so show both steps. Don't skip over showing to 1 centimetre cubed. Don't just do it on the calculator and stick the number in your answer. Now the last part. Part number 4. The concentration of the sodium thiosulfate solution in grams per litre. Now this one's a dicey one because look, of its crystals, Na2SO3.5H2O. Sodium thiosulfate is hydrated. So what we're doing here is we're working out the grams per litre based on the whole thing. When you put the sodium thiosulfate on the clock glass, there was already water in those crystals contributing to the mass. So now we know what the moles of your sodium thiosulfate solution is. So that is 0.14 moles per litre. We want to find out grams per litre. So to go from moles per litre to grams per litre, you need to multiply by the RMM. Now the RMM is tricky here because the water contributes to the mass. Now don't skip this step. Make sure you show the examiner how you worked out the RMM because we'll be looking for this. So here, if I move that over to the side, we have Na2 S2O3.5H2O. 2 sodiums will be 2 multiplied by 23. I've 2 sulfurs plus 2 times 32. 3 oxygens, 3 times 16. Plus you have 5 waters, so it will be 5 multiplied by 2 plus 16 is 18. So it's 5 multiplied by 18. Then when you type that into your calculator and add it together, you get 248 grams per mole. Now, in this year, in 2015, you didn't get marks for calculating the RMM correctly. Sometimes you do, sometimes you don't. It depends on whether students are struggling for marks, basically. Now, back over to here. We take our moles per litre, which is 0.14, and we multiply by the RMM, which was 248 grams per mole. When you multiply those two together, we're going to get 34.72 grams per litre. And for 34.72, you get 3 marks. There are two very different titration calculations, but we go about them in exactly the same way. In a couple of weeks, I will be going through and starting the titration calculations on the Grinds 360 platform. So it's worth trying a couple more for yourself. And then if you're struggling with them, check in with the pre-filmed content that will be going up on the platform shortly. Now, hopefully that helped a little bit with your titration calculation. So if you have a good understanding of concentration itself, you're not going to have any problems with the titration calculation because they are all exactly the same. As you saw with both of those very different titrations with vinegar and the thiosulfate one, you start with what you know, you work out how many moles did you put in the conical flask. Then you use the ratio from the balanced equation to find the moles of the other thing, the thing that you're working towards. And then you find out the concentration of that. That will be the same first 3 steps every single titration. It doesn't matter whether it's water, whether it's dissolved oxygen, whether it's vinegar or washing soda or whatever else. They will always be your first 3 steps. So as long as you can read the balanced equation, I think that's the hardest part of doing that. And if it helps, draw yourself a little diagram with a conical flask, and I would actually write, what went into the conical flask? Okay. And then what were the other numbers that we added in as well? And then I would go from there. Hopefully we found that helpful.